Welcome to a video on surface area of revolution in parametric form. You may remember we did talk about surface area of revolution in rectangular form defined using this formula here when rotated about the x-axis. And we use this formula here when rotating about the y-axis. So when the equations are in parametric form, we'll just use a different variation of these equations. Meaning we'll have the same formula, but ds will be defined as the square root of dx dt squared plus dy dt squared dt. So to determine the surface area of revolution in parametric form, we're going to use these formulas here. So one of the main things we have to remember is when we rotate about the x-axis, the distance from the curve to the x-axis is going to be y. And if we rotate about the y-axis, the distance from the curve to the y-axis will be equal to x. Let's go and take a look at some examples. We want to determine the surface area of the curve rotated about the x-axis on the interval from 0 to 2. To save some time, I've already graphed the curve on the coordinate plane on this interval. Rotating about the x-axis would produce the surface as we see here below. Since we're rotating about the x-axis, we know the distance from the curve to the axis of rotation would be equal to y, as we see here in the formula. Let's go ahead and see if we can apply this formula. The surface area will equal 2 pi times the definite integral from 0 to 2 of y, which is 4t, times the square root of dx dt squared. Well, dx dt is going to be 2, so we'll have 2 squared plus dy dt squared. Well, dy dt is 4, so we'll have 4 squared dt. Let's go ahead and simplify this. This is going to be the square root of 4 plus 16, which is the square root of 20. Well, the square root of 20 is 2 square root 5. So 2 square root 5 times 4, that'll be 8 square root 5 t dt. Let's go ahead and factor this constant out. So we'll have 16 square root 5 pi times the definite integral of t dt from 0 to 2. So we'll have 16 square root 5 pi. Well, the antiderivative of t is just t squared over 2. Now we'll go ahead and evaluate this. When t is 2, we'll have 4 over 2, that's 2. And when t is 0, we'll have 0. So the surface area is going to equal 32 square root 5 pi square units. Let's go and take a look at the same problem, but now rotated about the y-axis. So it's the same curve, the same interval, but now rotated about the y-axis. So now the distance from the axis of rotation to the curve is equal to x, as we see here in the formula. Let's go ahead and see if this affects the surface area. Well, x is equal to 2t. Of course, dx dt and dy dt are the same. And the interval is still from 0 to 2. This is square root 20, which is 2 square root 5 times 2. That'll be 4 square root 5 t dt. Again, let's factor out the 4 square root 5. So we'll have 8 square root 5 pi times the definite integral from 0 to 2 of t dt. So we're going to have 8 square root 5 pi. The antiderivative of t is the same as last time, t squared over 2. So when t is 2, we'll have 2, and when t is 0, we'll have 0. So now the surface area will be 16 square root 5 pi. So if we take this curve, rotate it about the y-axis to create this surface, the surface area will be 16 square root 5 pi square units. Let's take a look at one more example. Here we want to determine the surface area of the curve defined by these parametric equations on the interval from 0 to pi about the x-axis. So here's the graph of the curve on this interval. So if we rotate this about the x-axis, it'll produce this sphere. And then once again, notice the distance from the curve to the axis of rotation here would be equal to y, which we find in our formula. So this definite integral should give us the surface area of this sphere with radius 2. Let's go ahead and try it. The interval is from 0 to pi. Y is equal to 2 sine t. And then we're going to have the square root of dx dt squared. Well, dx dt is going to be negative 2 sine t squared plus dy dt squared. Well, dy dt is going to be 2 cosine t squared. Now let's go ahead and simplify this. This is going to be 4 sine squared t plus 4 cosine squared t. I'm going to go ahead and factor out the 4. So I'll have 4 times sine squared t plus cosine squared t. Now here you probably recognize sine squared t plus cosine squared t as 1. So this becomes a square root of 4, which is 2. So we have a factor of 2 from this, a factor of 2 here. So let's go ahead and factor out of 4. So we'll have 8 pi, and then the integrand is just sine t now. This will equal 8 pi times, well, the antiderivative of sine t is negative cosine t. And now we'll evaluate this at the upper and lower limits of integration. So we'll have 8 pi times negative cosine pi. Well, cosine pi is negative 1, so the opposite of negative 1 is positive 1, minus, well, cosine 0 is 1, and the opposite of 1 would be negative 1. So we'll have 1 minus negative 1. That'll give us 2. 2 times 8 pi is 16 pi. So the surface area of this sphere is 16 pi square units. Of course, this surface area should be the same if we use the formula for surface area of a sphere. In the last example, the radius of that sphere was equal to 2. So using the algebraic formula for surface area, we would just have 4 times pi times 2 squared, which of course is also 16 pi square units. Okay, that's going to do it for this video. I hope this was helpful.